Okay, let's get started. I'm going to give a quick intro on myself. Well, who am I? I'm Ezekiel, Gen Y series, which would be 1981, 96, that generation. I'm really being fortunate to be educated on an institute named NTTF. It's an Indo-Swiss collaborated polytechnic thing. The difference is they believed 75% of practical and 25% of theory. So that is my base education, and on that, the bachelor's came from Lincoln University. Part of Data Patterns. Data Patterns is a company of Indian origin, majorly into defense and aerospace. The best company to start a career, not so great from money aspect, but very nice platform where you would learn tremendously and non-linearly. So I started my career with Data Patterns. Then I have had a small stint, and in Data Patterns majorly, uh, as a fresher, we were given privileges to work on very high-end technologies. Have developed for NSTL a torpedo fin control of a BLDC motor. That's the smallest Indian-made torpedo fin control system. I've been part of it. The Mark III vibration shaker is our design, so which means whenever a satellite is getting launched, after the full assembly in VSSE, the platform goes into a vibration shaker which simulates what it is expected to have in the space. So that full design is from Data Patterns, and I'm glad that I contributed to the design of it. Then it is a dual stint on Honeywell. Further to Data Patterns, I joined in Honeywell with their advanced technology group, and then came out to Intel for about 4 years of time. You guys are really tracking the processor tech. Do you know which is the latest Intel processor which is out in the market? No, i9 is only a series. We'll get to that. But which, like you have Panther Lake, you have Meteor Lake, those kind. The latest one is Panther Lake. So the Panther Lake has NPUs, which is AI enabled. That platform is validated when I was there with Intel, and I'd been glad that the complete advanced enabling platforms were validated by my group. I had about 15, 20 real good engineers, and it is presently hit market. I think Acer has launched the first product with Panther Lake as the brand. With Honeywell Aerospace, it's been like close to about 15 to 18 years in Honeywell. I started as a hardware designer, slowly moved into a little part of control systems, and then got into high-speed digital design. That was where my experience was about 12 to 13 years, and then I decided to get into systems engineering. So we will get into what is systems engineering in a bit of time. And further from there, presently I am being a principal engineer for Honeywell Services and Connectivity Group. This is a group who does a lot of activities with satellite communications, gateways, enabling cybersecurity for the aerospace platforms. These are new trends which are picking up. Aerospace is picking up cybersecurity very new, and I'm being part of that group. I also play as an associate chief for Honeywell International for one product line, and that is a bubble assignment which is on me now. It's a privilege that I've been an inventor for 14 United States patents. And patents, if you see, when you have subject matter expertise coming into your career, you normally tend to have a monopoly of patents in one single subject. But systems engineering is all about getting different domains engineered into a product which is getting into shape later. So that way, the patent portfolio I have is diversified. I have something on night vision goggles, something on power electronics, something on software, on cyber security, and so it is diversified. So about 14 United States patents. Close to about 2 decades into hardcore R&D of aerospace and defense sector product lines. That is me on the career side. On the other aspect of it, I'm a certified pranic healer. How many of you know what is pranic healing? Awesome. How come you know you are into it? Okay. So pranic healing is all about energy healing. So it's a complete 180 shift on technology. It doesn't go by what belief you have on the analytical brain. It is the other side of it. So I'm a certified pranic healer. I'm a collector of about 1,000 varieties of rare medicinal plants. We were chosen as the Vanamitra Awardee for 2023 because of the ecosystem we have built. We have a complete integrated farming system. And I'm a happy dad for two kids, one at the 7th grade and one at the 4th grade. Still learning, trying to clear off my supplies in life. With your generation, supplies is supplies itself, no? Supplies is when you flung a subject, you call supplies. It's the same, okay. And I'm dyslexic, and I'm glad for it. Dyslexia is a situation where your hold on vocabulary, your hold on grammar, spellings are real bad. Why I'm glad for it? Because in the same time, it's a weakness. It gives you a small twist to your creative part of the brain, which is not very common in the technical side. So that blend of little bit of creativity, I'm not a great artist or so, but a little bit of thinking off the box is given by this weakness which I have. And that's really helping. In a technology field where you're fully analytical, having this bit of it is good. Now, you might be thinking, why so much of self-intro? It is nothing to say what is that I am. It is more to get a human connection to the crowd I'm addressing. Second part, if you see, you would see some of the items being bolded. And I wanted to pass a message back into you that life is not all about what are your achievements. If you see, the achievements are all very lightly written, but the privileges what you have to be grateful for it. One part, education is a privilege you have. Not everybody get it. You being here is a real privilege Almighty has given you. So getting to feel great about it and having mindfulness about it is a real need of your life, and this part of it I want to inculcate in your thought process. The second aspect of it, having wonderful teachers. Having wonderful teachers that after 20 years, when you look back, you say that this person has made a change in my life and the way I think and I work is a real privilege. So getting mentored by wonderful faculty, getting mentored at a wonderful institute is all privileges which you take for granted, which others don't get. So embrace that. Third, it is 100% known to me that the opportunities given to me are not because of my skill set or my abilities, but it came to me as an opportunity by luck given by Almighty. There are 200% guarantee that there are much higher skilled people who, if would have got these kind of opportunities to work, would have flared. But the opportunity is given to me. So we have to be grateful for the opportunity what we have got. So that is the other part I just wanted to transfer in. Apart from all this, if life is all about money, career, and other things, that is not. You need to have one side of your life which actually takes care of your interest, your passion. Work could be a passion, and luckily in this case, I like technology, so it is passion to me. But apart from that, there are very important things that life is not about money, life is not about career, life is not about your success. It is also about, are you doing what you like? Can any of you be bold enough to stand and say that I've got a weird hobby, I'm really happy and glad that I'm having that hobby? Anybody? Hobbies? Hobbies which are distinct and little towards the not normal hobbies. Anybody here? Are you into pranic healing? Your dad is into pranic healing? No? Okay. So it's important to have picking up on stuffs which are little differentiated, which keeps your mind fresh, so that when you have the tussle and the stress of work and life and family and other things, you have one section of it which keeps you a healthy mind and a healthy human. So that part is important. Equally, it is also important to be a learner continuous your life. If you don't make a new learning, it need not be academic. It need not be very specific to your subject. It can be moral. It can be about relationship. If you're not having that learning in more than 2 weeks or say, your life needs to be replanned. You have to go into that situation that every now and then you keep a keen learning mind, and that keeps you fresh. Foremost, it is important to know your weaknesses. Not everybody comes with only strength. And it is important to know that those weaknesses are given to you by Almighty, and you have a flip side of it which could be turned around as that weaknesses becomes your strength. So with this, I will get into the actual subject. Any questions on this? Any clarifications? Cool. So they are normally owned by government institutes, and that is where that G came in. Otherwise, the function is basically navigation satellite systems. What is it supposed to do? It is supposed to provide precise positioning, navigation, time seeding, and PNT services globally. So the intent of this as a problem statement is you should have a mechanism wherein a receiver part in your hand should be able to exactly tell on the sphere where you are. So that is a problem statement for engineering. When you look at GNSS, GNSS originated from, the first GNSS came in from US. It was named GPS, came somewhere in 1978. It was specifically made for navigations for military. And they did this good thing that they made a low-end version of it at the same time available for the public domain to actually exercise. And by then, Russia got to know this and they were not in great terms. So before even I start, why did I select GNSS as one of the technology where I want to talk to you? Because this engineering solution has transformed life fully out of the technology forum into the common man. My mom, when she wants to go from one place to the other place, with zero connect to technology, she looks at, sees traffic, she finds the best way, and all that is possible by GNSS. So from an engineering field, if an invention has a novel cause and a novel effect, this is one of that great idea which was brought in and it's still helping and going on. So it happened that US came up with this GPS infrastructure in 1978. Russia responded to it by 1982 with a global coverage and named it as GLONASS. Then came a situation of technology adaptance, or what happened is somewhere in 2000, US made the decision that what was that precise GPS capability was made public, free of cost. So then what happened, everybody started experiencing the benefit of it and they started adapting it quick. So further from 2000 to about 2013, you see that the gap of bridging is suddenly shortened and all countries started bringing out stuff. And that majorly happened because at this time frame, GPS was made global, free, and with high accuracy. So Baidu was a response of it from China. They came out in 2000. They were globally reachable. Then came Galileo. It was an European Union's response to this GNSS situation in 2011. Japan responded, but they weren't in that great shape to have the complete global coverage. So they came out with QZSS somewhere in 2010. And we came into existence naming IRNSS. That was the initial name. Do you know what is the present name of the GNSS solution from India? No. It's called NAVIC. It was initially named as IRNSS and then it got renamed as NAVIC. So that came into existence 2013. So this also tells another story. This also tells, because of the geopolitical situation, how a technology has ended up in spending a lot of money unnecessarily, because you already had a full-fledged solution here. Now, if world was in harmony, these existence and these expenditures weren't really needed, because if that was made global, the other things are just repetition of it. So with that, that being the top privilege, the top peripheral touch on GNSS, we are going to take the GPS and the others are almost similar technology and deep dive into this part going further. But before we go further, as engineers, we need to ask a question before a technology is known to us, that if this is given as a problem statement to us, that you need to have a mechanism wherein a cheap receiver should be able to pinpoint and tell where do I stand on a sphere, the sphere being the globe, what would be your thought process of getting that technology on? And we'll pause for a moment, we will hear from you and then make further proceedings. So the question is, if a problem statement, an engineering problem statement is given to you, think of it that you have a sphere, which is the globe, and in this globe, anywhere you are supposed to get a receiver which receives something, that is what you are supposed to bring up an idea, on telling the receiver itself that I am at this point very precisely. What will be your engineering response to that? Let's give a little bit of thought process there. Anybody? You don't have to shy, because tomorrow I'm not going to see you and you're not going to see me. So there is nothing we are making very formal here. Be very transparent, open up to any ideas, and any discussion is good. So somebody, even the very non-technical thought is fine. If a problem statement is given like this, how would you brainstorm and say top level, I think the system should have these characteristics to achieve that? Anybody? You? Yeah?
I will first calculate the distance between me and the distance what I want to find.
You will calculate the distance between you and a known point, which is a satellite. Good.
Then I am going to use any IoT device or any satellites to share the information from me to that point.
You will use an IoT device to
Satellites.
or any satellites to do what?
To share the information from my point to that point.
Very great thought. In short, this GPS and GNSS came in of brainstorming for about 6 months, 12 months and all. You are giving a very nice idea. In survey, there are two aspects. Triangulation, is this known to you? Triangulation, raise hands. No, I don't have time. I'm being given a time check. Do you know what is triangulation? So triangulation is about what the other person was talking, of finding a precise location on any three-dimensional axis, a position of one item by looking at it from 3 or 4 views which have known coordinate system in that axis. So which means if this is the point where the receiver is and you set 3 or 4 points in the axes with a known coordinates, and from there you try to see and measure the distance to that, measure the angle to that, and that angle measurement, once you convert into trigonometry, would be able to give you the coordinates of this system. So this is called triangulation. This is used in survey. Your first sem, you would have gone through this. Really? Okay. So this is one method. But the problem here is, it is more sensitive to an angle. So the way, if he is the person who is receiving and you and ma'am is looking at him, there are 3 angles at which we look at it. Those 3 angles and the coordinates of us being known, you could do a trigonometric correlation into finding the coordinate of that person in the same plane we are in. If it is a different plane, altogether different story, but in the same plane, that would be doable. The other stuff is called triangulation, trilateration. Trilateration is exactly what he was speaking about, but he was speaking more from a single point. So trilateration is about, again, the fixed points are all 3 of us and he is the receiver, but instead of measuring angles, I try to measure what is the distance between me to him. So if I am a point in the coordinate system, he is a point in a coordinate system, how do I expand my distance periphery? Do I expand it as line or do I expand it as sphere? Sphere. Why? Because I am omnidirectional. The point could be even behind, the point could be left or anywhere. So I expand my distance correlation in spherical way. So when I expand, at one point of time, my sphere will actually interact with the point there, right? When I am a point, I extend, and at that point, the sphere is going to intersect. Same way, the projected sphere from her and the projected sphere from ma'am also gets and coincides. So 3 spheres try to coincide, and that would give 2 points of merger. Now this 2 points of merger, why? Because we are talking 3-dimensional. Now there is a known part that the point we are referring is on the globe. So the other point which is intersected on the top happens to be a hypothetical point much above your altitude. So you are at altitude 0. The other intersection would happen much above you, right? So this is another method used. Now the benefit of this is, you don't have to be really sensitive about angles. You only need to have a measurement of distance to the other person, the other point and me. And it can be one direction. Because if he is able to look at me and say that I am this far, and if he is able to look at ma'am and if he is able to look at her and say that I am this far, then he would be able to decipher the coordinate system himself. Whereas the other ones, it is difficult because it is more sensitive on a plane for angles which is difficult to maintain. So it was taken as trilateration should be the method a GNSS should be approached. That is what the experts decided. Clear on this part? Now, how do we measure the distance remotely? If I have to measure without a scale, distance between me and him, how do we measure it? The easiest way. Who is that? Get up, no? I might sometimes overlap 12:30, okay? We don't know. So the easiest method is, let's say we take a bolt, tie a thread and throw it to him. He catches it and later I mark the thread length and bring it back and measure the length remotely without touching him. I am able to measure. I need not have a tape or scale there. Or little forward thinking is, if you have a known speed car, I have a remote car, I know the speed is fixed, I drive it from here to there, it takes about so much time, the velocity is known, I can decipher back how much is the distance, right? Or going a little further there, instead of car, if I put a sound wave, I say hi, and it has its own speed in space, it reaches there. Now when I say hi, instead of saying hi, I say hi at 11:58. I've given my time and I'm talking to him. So he notes it down, and he also notes it down that when he notes, he also notes his time. Okay? So what would be his time minus my time? The time of flight to get there, right? So with that, I know that speed is known. I know the delta time. I can correlate back the distance, right? So one more step further. Instead of sound, let's use light. Why light? Because light is super fast. What's the speed of light? Awesome. So with that, if I flash a light and at that flashing I'll encode my time also into the light, he receives it, he would be able to decipher back the thing. So that becomes the fundamental for GNSS to work, right? And we were talking, this was the exact thing. So your brains are actually working because this is what they would have gone through that time. This is about, is it a two-way tracking or is it a one-way tracking better? So the two-way tracking would be that you send something, it bounces back, and then you have two-way travel time, and from that you take half of it, you get the distance. The other one is, you just send the time, say hi at 11:58, the other guy receives and notes his local time, and then you can get going from there. So these are two options. So we said trilateration is the base. On that, we are going by this. Cool? All right, okay. So the bigger problem is understood. The top level approach is understood. Now let's get into a little bit details of, we said, no, we will deep dive into GPS. That's what we are going to do. So the GPS basically has three segments. One is a space segment, one is a control segment, and one is a user segment. Now the space segment is all about the satellite infrastructure. When you have the globe and you said you wanted to have 3 points, you have to have a situation that all coordinates, the latitudes on a globe, has to be addressable. So one way to do it is bring swarms of satellites around and make sure that those stationary satellites always have visibility to all the probable points, which would be too much of an expense because Earth is big and having satellites to cover everywhere statically would be difficult. So there was discussions, and the discussions were on orbits. So are you aware of the orbits called LEO, MEO and GEO? You are. Okay, so you are or you are not? Okay, let's go in. So LEO is about low Earth orbit. This is from the globe, any distance which is in about 100 to 200 kilometers is treated as LEO, 2000 kilometers. Further from 2000 to 20,000 is treated MEO, and GEO is anything further than that. The GEO is always stationary. MEO and LEOs are orbits where the satellite is supposed to revolve, and the revolving time in an orbit of LEO is about 1.5 hours, and for MEO it is about 2 to 12 hours because of the distance we are in, right? So a discussion was there, and an engineering problem is being put. Which should be the selected one? What will be your response to it? Which is the best? We know trilateration is what we are supposed to do. We knew that it is one way. Now we are being given as engineers that we are deciding LEO, MEO or GEO. What would be your take there and why?
Geo because it's the furthest away, so you can easily see the larger position.
Very good. Anybody else? Anybody thinks that LEO is good? No? Anybody thinks MEO is good? React, no. I'm getting bored. Cool. So he was telling a good point that if you are GEO, you are very far, so you don't need to have so many satellites. Good point. But you also have a problem. The distance from GEO to you is very far. So a small error happening in my measurement is going to screw up my actual calculation. So you're very far. The problem with LEO is exactly opposite of what you said. When you are very near, your visibility is less, you need more satellites. So then a middle path was chosen. The middle path is MEO. It has the goodness of GEO, it has the goodness of LEO. So the orbit was chosen to be MEO, and MEO has its orbit time of as 2 to 12 hours, right? With this 2 to 12 hours, and we are far like 22k kilometers far, with the speed of light, your flight time is close to about 110 to 130 millisecond. Why is this important? Because as engineers, we are now deciding which is the orbit we are putting the satellites. Don't think it is already made. We are making it now. So then, to correlate the user's perspective, what will the user use it for? The user will use it for navigation, guidance and other stuff. And normally, our speeds on ground and speeds on air is not heavy that in about 110 to 130 milliseconds, it make a Zameen Asman ka farak, right? So it is a decent thing that your flight time is 110 to 130 because that is the minimum response time I would need to get some information onto me and then predict on it. So this is being selected. Now in that selection, there are 6 orbitals which are being selected geometrically. We will not get into details. It is more of a 3D space geometry. So from the equator plane, with about 50 degree of angle, 6 orbital planes were defined. And on that, 24 channels of 24 satellites were put. So that means in one orbit, how many satellites? 4 satellites. 6 fours are 20. 6 fours are 24, na? Yeah. So 24 satellites are being put. Now each satellite has an atomic clock. Anybody is aware of what an atomic clock is? I'm going to stop. If you're not speaking, I'm going to stop. At least say no if you don't. Okay, so atomic clock we will get into some time, okay? So because it is very important, your velocity is much higher, your time of flight is very small, so you are supposed to make very accurate time measurements, which means your time keeping stuff should be very accurate, and that is why atomic clock comes in. So with atomic clocks, things are in. Now if you see the right side GIF image, that kind of explains, you're able to see? This kind of explains what are the orbitals we are on and what is the hypothetical point we are trying to look at. And when you see the hypothetical point being stationary on like this point where I am standing, assume that this it is. If you look at the satellites which are revolving at about 12 hours for one full revolution, you will see that at any point of time, because of the orbit we have chosen and because of the orbital planes we have chosen, we at least get about 4 satellites all through the time. Visibility. Why 4 satellites are important? Why is an engineering decision made to ensure that this kind of a configuration is put to make sure at any point of time 4 satellites are needed? Because 1 point defines a single point on the Cartesian system. 2 points defines a line. 3 points define a 3D space. So you are now in a 3D space supposed to do trilateration. So you need at least 3. The 4th one, why is it needed? Is because your time has to be exactly synced. He and me should be in the same time sync. Otherwise you get into errors because your velocity is much higher. So the 4th satellite comes in from that angle. So you see that, you see that at any point of time it is 10, 8, 9, all that, blah, blah. But at minimum, there is guarantee that 4 satellites will be visible. Cool? Any doubts? Going well or going boring? Cool. Now we're going to talk about the control segment. How many of you are good in software? Who likes software? C? You're good. There's a question for you, okay? Coming down. So we are now talking about the second segment, which is the control segment. Now in idealistic first order system approximation, you don't need the control segment, because if everything is well set, nothing deviates, everything is perfect, you don't need the control system. The control segment. The control segment is an approximation of GNSS over a third order system. What is first order, second order and third order? First order is a very linear, very predictive system. Second order is the quadratic nonlinearity is coming in. Third order is the other highest nonlinearity coming in. So this control segment is only needed when you actually take the practicality. As engineers, it is very important to know you started designing the system as first order system, where you just said triangulation is good, measurement of this is good, all that is fine. So that is the first order definition of a system. But then you get into a realization that my system is not first order. My system has nonlinearities. My system has deviations, drifts. So there you try to see the characteristics of it from a second order aspect, the nonlinear aspect. Then you get into the thing that bloody, it's not even non-linear, it has got its own polynomial level nonlinearity. So that is where the control segment is put. Control segment is all about, at Colorado they have a receive, and in that they look at all satellites, look at their health, and with that health and with the slight adjustments needed, there is backfiring of data which is sent to the satellites to course correct their transmissions. Okay? To course correct their transmissions. So that will take care of the non-linearities you are getting into. So this is the control segment. Then comes the most fascinating part of user segment. User segment is the receiver you have in hand. Your mobiles have GPS receivers. Your earlier car stuffs have GPS receivers. But the aspect to be really apprised here, when it started, that was the GPS receiver. It is probably this podium big and doing the same job. But over 3 plus 2, 5 decades, you are seeing a rice grain equivalent exact replica of that. So uBlocks is a company who are really pioneers into GNSS solutions. They have made a rice grain big GPS receiver, which is that tiny. Now, I cannot go without talking about Honeywell in this. So Honeywell is also playing there. Honeywell is playing as a GNSS receive side, but we are way different than this segment. This segment is all about miniaturization, cost effectiveness. It is more about addressing the bigger crowd. But Honeywell plays in aerospace on a different segment where safety is utmost, where when you fly, your life is dependent on this. So Honeywell brings in something called design assurance level DAL-A. So this GPS receivers are DAL-A GPS receivers. They do the exact same function. It is like Mercedes and Nano. Both are cars doing the same. But Honeywell plays it much bigger. The assurance that this will work in all the odds, the assurance that the non-linearities are much predictable and deterministic is there with the global navigation systems of Honeywell. Cool? So we talked about user segment. We talked about what segment? User segment, control segment and space segment. Cool. Now this is a good place to slightly pause. Now somebody said she is good in programming, right? So just to slightly clear off your brain back into track of boresome. If you are being given with a situation that you are supposed to write a program without using any conditional statements, if, else or anything, neither using any logical operators, to fetch a number and print it as odd and even, how would you attempt it? Question is clear? Very simple question. Write a program to fetch a number, print it out as odd or even, but you are not allowed to use ifs or any logical operators. You are not allowed to use any conditional operators. Anybody? Yeah. No, loop is again conditional only. No? I mean, it kind of senses a situation and then breaks off. So, anything else? Yeah, you're writing something on the board. What is it? Speak on. Speak on. I'll come back to you, okay? I'll come back to you.
I guess I can do using C programs.
Yeah, you can do it with C, but the constraint given to you is you are not supposed to use if and any logical operators. If, else, for, while, not allowed. How will you do it?
I guess I can write header files. Is A,
Uh-huh.
and then between brackets enter the number.
Huh?
We accept the user.
Cool. Okay, you have something? No? Okay, so I'll take it to this level. Does this give any hint of how you're going to attempt it? What is this basically? What is this? Pointer array. Okay? So that has even and odd. Does it trigger any thought process that how can you address the problem statement if I get you till here? There aren't good programmers here. Okay, cool. So what happens is you take the number, take the mode low, and that mode low, if you index it to the pointer, what will happen is automatically either this gets printed or this gets printed. So you don't have to do anything. This is just to ensure that if you give a negative number, they get multiplied, so the mode low -1 becomes +1. But apart from that, directly take the mode low and put it as an index on that pointer array. So what will happen? Either it will be 1, any number divided modulo 2 will give only 2 outputs, 1 or 0. If it is 0, it means it is even. So you are not using any logical operators. You are not using any conditional operators. You are just printing it as an arithmetic operation and then getting to go. So this has nothing to do with what GNSS is, okay? This is again just to bring back a shake on your brain and then bring back your concentration back. Cool? So now, we will quickly time check. How much time more? Okay. One question. Till time, whatever we have discussed, is it just gone as a talk to you or is it gone as a thought to you? Talk? Thought. Yeah, good. That is where I wanted to land. Now we are looking at the spectrum where majorly the GNSS is flooded. So if you see that I've listed all the GNSS solutions, we will be talking deep diving on only GPS. So GPS has 3 segments, L1, L2 and L5. Primarily the trivial and the most older technology is L1 and it is still supported and we are going to concentrate more here. Okay, so we are talking about a band which is 1575 megahertz. Your carrier wave is 1575. You are into RF already? Ma'am is teaching you? No. So they are not being introduced to RF?
Now they are in the third semester.
So which sem?
Third sem.
My bad. Which sem would they pick on RF?
Fifth sem.
So they are not even aware about FM, AM modulations?
Analog electronics, they would have studied now.
Third sem it's there?
Electronics, it is there.
Okay, no worries. We'll deal it. So, Red FM, what is the thing what you tune into? Red FM is what band? FM it is, yeah. But which band you tune into? 93.5? 93.5 Red FM, huh? Okay, good. So that is the carrier frequency we are talking. And this transmitter is also like a radio and they have different carriers. And what I'm going to speak is 1575 is the carrier chosen for L1. So we are not going to dwell deep because you have not got the basics of RF now. I'm going to skip. But what I want to say is there are 2 bands, upper bands and lower bands. And all the GNSS solutions have their spectrum very well defined. Some coexist, some are differed, but it is around this band of 1164 to 1606 megahertz everybody is transmitting. Okay. Now, a cool fact to look at. We said that we have put the satellites at about 22K away from the globe. Let's look at the long journey the GPS signal is taking. So from 22K to about 0 where your receiver is, you travel 3 segments specifically from an RF world. So have you seen in your house you have 2.4 gigahertz Wi-Fi and 5 gigahertz Wi-Fi? What is good in 5 gigahertz Wi-Fi? You get real speed. But what is good in 2.4? 2.4 gives you range. Okay? So that means the attenuation or the lowering of the signal over a distance has a correlation to frequency. So when you are traveling about 22K of kilometers, the signal travels through multiple mediums and each medium does something to the signal itself. Okay? And luckily, the major part, which is from 22K to about 1000, you're blessed because it's space, there is nothing too much affecting you. It's a straight free space transfer. So your signal gets almost very decently till here. Then you are hit with one part of the atmosphere, which is ionosphere. The ionosphere is rich in which gases? Nitrogen? Yeah? Oxygen? Carbon dioxide is there? Huh? Well, maybe. Now it is there? Okay. So be it. So we have multiple gases, but there is also something phenomenal about the sphere. It is the maximum sun's radiation happens there. Because of that irradiation, the oxygen and nitrogen turns to its ionic state, which is ozone. And which is the ionic state of nitrogen? N plus? Whatever. There is a state. Now these ionic items has capability to interact with your RF transmission. It is more like a prism where you enter from air and then you get diverted, and that diversion is called, what is it? Refraction. So there is a refractive index given by ionosphere for an RF energy because there are ionized elements there, and because of that it gets slightly diffracted. So it takes a different path. So your distance may be wrong. Then you get into a situation of troposphere. Troposphere is, so your major travel was very easy. You got troubled here to some extent. This is an obstruction but not a great obstruction. It does something to the signal but not much. But then the tail end point, which is, we said 50 to 8, right? That is where your troposphere finishes. Then you have the landing area. That is where the geometries, the metallic objects, all that starts giving you trouble. And what trouble they give? They give trouble called multipath propagation. You are supposed to get only one signal, but because it gets diffracted, you start getting into multipath. So you will get same information from 2-3 places, which means time is differing, and that brings a dilution of time. And when your time is diluted, your accuracy is diluted. Okay? So that's the long journey from transmitter to the receiver. Let's also look at, he was talking about let's just bombard it with a lot of energy. You are mentioning, right? So that way, when you look at GPS, we are going to talk more about the L band. Approximately about 125 watts is being transmitted. 125 watt is a huge power for an RF transmission. Not so great with normal powers, because 125 watts is what? 2 bulbs. But for an RF transmission, it's a huge power. With that power, it exits out of the, you want to yawn? You getting sleepy? Okay. So it exits out of the transmitter. Once it exits out of the transmitter, 22,000 kilometers when it travels, there is something called free space. What is it called? Free propagation, free space propagation attenuation. So when you travel 22,000 kilometers, if you know the frequency, you can predict how much the signal will become weaker. It is easier now to switch to dBs. So we are talking about 125 watts. 125 watts is about 50 dBm. dBm stands for decibel with reference to 1 milliwatt. Okay? So 125 watts, if we are not into RF, just get it plain. 125 watts is equal to approximately 50 dBm. Now this 50 dBm incurs a 180 decibel attenuation. 180 decibel attenuation. So 125 watts gets 180 decibel attenuation, which equates to 130, which means what we are supposed to do is 50 minus 180. Okay, so that gets you to about minus 130 dBm. You know what this minus 130 dBm is? This minus 130 dBm is 0.001 picowatt. What did we transmit? 125 watts. What did we get? 0.001 picowatt. It got attenuated to almost zero. No signal is reached. But, and to give you an analogy, this is almost equal to 1 billionth of a radio transmission power. 1 billionth. Have anybody done an radio transmitter as hobby by yourself? No? Guys, you got to gear up, man. You are electronics people. You are supposed to do some radio transmitters. You are not even getting into the subject. You get so many kids. When you eat the fourth pizza, no, we call it as a nibble concept. The fourth pizza you eat it on electronics. Buy some components, make something, let it not work, well and good. So when you have nibble pizzas converted, no, you will start getting the taste of that electronics pizza. It's really good. Try that out. When you eat the fourth pizza, spend the fourth pizza's money on some electronic components. Make some transmitters. And then you will understand how difficult is it to tune a transmitter. How difficult is it to receive a transmitter. So I'm just saying, I was thinking that somebody would have done and they know the pain of making a normal radio work. So you are at 1 billionth of that, which means it's a very tough situation to receive. Your normal noise floor itself is, what is the atmospheric noise floor? Much above this, no? So we are above, and this is digged deep into the noise floor. And that is what you are supposed to receive. Cool? So we are put with a next problem statement. How do we deal with this? We did all the goodness of putting a remote station, put out 125 watts. But unfortunately, after all the journey, what I'm hearing is I'm only getting about teeny tiny power at the receiver. And which is also buried down. Now to give a context, assume that all of you are talking to each other. Okay, that is a noise floor. You are talking, everybody is talking to each other. Will I be able to tell what she is talking to him if everybody is talking this way? Difficult, na? Because it's noise to me. I cannot receive it. But I put a law that when you talk in one dialect. Either two persons talk in Malayalam, two persons speak in Kannada, two persons speak in Tamil, two persons speak in Telugu. And if I put that rule and if everybody obeys that, all of a sudden I start to get a selectivity. That in the noise floor, if I know my dialect is Malayalam, I can easily pick up words much better. So the noise floor, even though it's flooded, they are no more talking the same language. They are talking different language, or they are talking different code, different dialects. So that is easy to be taken and individually concentrated. If she is talking and saying hi in English and all of you are actually talking Kannada, it's easy for me to say that she said hi to him, right? So that is the trick we are going to make it work here, okay? So we have a problem, and how we are going to face it is by putting a dialect into it. Now before we get into it, just look at how a receiver would be seen as a GNSS receiver. So you have the antenna, you might have some filters to avoid off the, yeah? Somebody? No. Okay. You have to avoid some non-sensitive signals left and right. So you take the clean signal, you do a pre-amplification. Why is pre-amplification important? To strengthen what? To strengthen the vehicle signal. But what is the problem with pre-amplification? When you amplify, you are also amplifying the noises. So the overall noise floor is lifted. Correct? Because you are very selective to that band. In that band, there are a lot of noise. So when you amplify, you get in. Then you do a down conversion because you were on a very high frequency, which is hard to process. You do a down conversion. Then you do an analog to digital conversion. Then you get into acquisition. Once you get into acquisition, there is one stuff we earlier decided that there will be 24 satellites and they are all transmitting the same frequency. So after you down convert, the down converted signal has information about what? It has information about all the visible satellites. So now you cannot go and say that I talked about. So which means after acquisition, it is supposed to look at the same signal from different aspect to see that which all satellites are now giving me information. Not all 24 will be. But you don't know which are all those 5 satellites which are going to talk to you. You know there are 24 satellites. You know about the information where they are, but you don't know which are now talking to you. So you start with a blind mind to start looking at all the 24s at the same time. Now we talked about that dialect, right? That dialect in RF world is called code divided CDMA. Okay? There is time divided, there is code divided, there is frequency divided. We are now talking about CDMA. So CDMA is that you make a pseudo random number, and that pseudo random number you actually XOR with your message, get the intermediate stuff on, and then put it to a carrier wave, which is that 1575 frequency we were talking about. Mix it and throw it off. So once you get, each of the satellite has its own pseudo random number, which is very deterministic. The pseudo random number is only pseudo and random from the selection point. After that it is fixed. It is not changing every now and then. So there are 24 pseudo random numbers. They are called PRNs, and that PRNs along with your message is reaching you. So now you start looking, because you know all that 24 pseudo numbers, you start looking in the noise floor whether satellite 1 has pseudo number 1, 2. So I will keep, if in this you are seeing multiple trackings, so one guy will keep looking whether I get the satellite 1's signal, right? The other guy will be looking at satellite 2's signal. And as soon as he says that I've got satellite 1, he locks on and says that I'm good. So similarly, you are supposed to bring 3 or 4 satellites. By then, you have the time calculated, you have the information of the satellite. From there, you can trilaterate your location. Cool? So this is about a little detail into what we were talking about. So we are talking about a message which contains the information about the satellite, where it is, orbitals, all that blah blah. You have the CA code, which is the pseudo random number. You are actually doing a modulo 2 operator, which is XOR. And then you are pushing it to the actual CW modulator, which takes the 1575, takes the signals, and this is the modulated signal coming out. Cool? So the only difference which happens between 24 channels is this information and this information changes. This information is a pseudo random number you have created. This information is the actual content of the message you are supposed to transfer. So the GPS satellites and receive communication via pseudo random number code. PRC has 3 advantages. One, we talked about the dialect advantage, and allows synchronization of satellites and receiver clocks. Cool. Now, this is a situation we were explaining about. This is a noise floor. You have all crap going on here. But the correlators which we talked about, that 24 items which are looking for, they tried to make a correlation. So this guy tried a correlation on this signal. This is his PRN number, but he is not getting a good correlation. He's only getting 1, 2, 3 hits, right? But look at that guy. That guy on the same noise is able to get more correlation. So he now understands that that signal is the satellite I'm supposed to track. Same signal made sense for this because the correlation value is more. The same signal did not make any correlation value here. This indicates this satellite information is visible and now you can actually track on it. Cool? So in doing this, you get a benefit, and that benefit is what you call digital gain in RF world. It's called processing gain. We transmitted how much watts? We transmitted 125 watts. How much did we receive? We received 0.001 picowatt. Very feeble signal under the noise floor. Now we talked about the dialect, one person talking Telugu, one person talking Malayalam. That benefit is now what we are going to reap. On the same noise floor, we are now reaping the benefit of correlation, and that gives a magical 50 dB gain. So the signal which was buried under the noise floor, after you have correlated, suddenly gets lifted of about 50 dB. And that 50 dB is equating to, so minus 130 dBm was our receive side, right? We did that calculation before. So minus 130 dBm we received. On that, the digital processing gain gave us 50. That 50 made it to minus 80 dBm. That minus 80 dBm is equal to 10 nanowatts. So we were talking about 0.001 picowatt without doing anything on the RF world, just by digital signal processing and correlation method, we have increased it to 10 nanowatt. Engineering marvel. CDMA is an engineering marvel. So now we are at a respectful power state to make assessment below the noise floor. You have lifted the signal. Cool? Doubts? We'll come, so we discussed about how we are lifting the signal. Now we will come to the other part. We made a wise choice of making sure the transmitted part to decide on your distance was light. Light comes with, not light, the RF world. It comes with lot of plus, but the negative is it's so fast. So when you are fast, to decide your distance travel, you have to be very accurately keeping your time. And that is the problem we are going to face now. An error of 1 by 100 second in a kind of RF transmission speed would equate a distance error of 1820 miles. So if your clock is screwed up, the complete thought process of how we attempted the problem statement gets screwed up, right? This is the second order kind of situation what we are getting into. So we need to have a solution for this. One part, we need to have a very accurate timing for our satellite segment. And that is doable. That is where the atomic clocks come in. But you cannot have that liberty on the receiver. Why? Because the receiver is in numbers. And receiver is in numbers, cost is a factor, affordability is a factor. So you have to turn around the technology to make sure that your receivers also get the synced time. And that happens by the fourth satellite we were talking about. When we did the triangulation assessment, we said that we need 4 satellites visibility, right? That is the reason this comes in. Now, atomic clocks, what are they? They are clocks which makes 1 second error in 10 million years. That means super stable clocks. How do we do this? We will get into it. So it's more a physics that how atomic clocks work. Cesium is an element, and the good part about cesium is it exits in 2 energy levels, one lightly higher energy and one lightly lower energy. Now how the atomic clocks work is, cesium in solid state is superheated. Once it is superheated, what happens? They become vapor. That vapored cesium has the yellow ones which are low energy and the red ones which are high energy, passing through a magnetic oriented tunnel, separates them because they are charged, right? And what is first done is, you knock off all the highly charged ones and throw it off. Bring the non-charged ones into an microwave chamber, you excite them with an energy, but that energy is based out of a quartz crystal's oscillation frequency. So how much of energy is being put is decided by the quartz crystal's oscillation frequency. So the high energy is gone, the low energy gets in, and as soon as you excite it, what happens? As soon as you excite a low energy atom, it gains energy and it goes as high energy. This high energy aspect gets into another diversion with a magnetic field. Then what happens? You divert the high energy one and that you count. This count becomes the negative feedback system for the quartz oscillator. Now how does a quartz oscillator work? The quartz oscillator works on a piezo effect. You excite it electrically, it vibrates mechanically. But the beauty is it's very tuned. But the problem is quartz crystals can sometimes sag and deteriorate. So as soon as it starts deteriorating, what will happen? The energy fed into the chamber reduces. When that happens, the amount of charged particles which exit out reduces. When that happens, the count reduces and it's a negative feedback system. So automatically additional energy will be pumped in here. So end of it, what happens? The oscillation of this quartz crystal will be kept super accurate. And based on that, you derive your clock. Cool? So that is about Atomic clock. I think, yeah. I think we have traversed through lot. We will slightly again reset our brain. We will get into a small circuitry. Why I'm doing this is, if you keep hearing all the jargons of the world, at a point you will say, bloody switch off. So we will turn back. And I do this, if it's you don't like it, we can skip it, we can get to the next one. But if you want a small, you want to attempt this? So the question is simple. The question is, you are into analog electronics, right? You are into op-amps. The question is, how do we derive the gain of an inverting amplifier? We'll take about 5 minutes in this. So anybody can come forward. If you are good, I don't want to waste time. We will get use of this time to explain and then get going. What is the gain of an inverting amplifier op-amp based? Loud, loud. Have a time check, man. Speak up. You want to speak? No. Anybody? They are covered op-amps when? What is the gain of an inverting amplifier? What is it based on that two resistors? Minus RF by Rn, right? So how do you derive it? We will quickly look at it. So the first thing as an engineer you ask, op-amp, what is your typical key characteristics? And op-amp responds, I will infinitely amplify the difference between the terminals. One of the character, right? He will always stand for it. First order system, we are not looking at second order, third order. First order system says that whatever you give across, I will amplify it infinitely. I will also have very high impedance that I will not allow any current to enter here. Input impedance, high. Second key characteristics. Third key characteristics is my output impedance is 0. First order system, not second order, third order. Now that is the commitment from the op-amp. The next question you ask is, you see a line going, you ask, what is this? And the guy says, I feed output negatively into input. So whatever is here, it is fed back into the input on the inverting terminal. So if I have an input going high, it means that automatically that will reduce the, if I have an output going high, automatically it reduces the input feed. So it is a negative feedback system, right? So that is the answer for the question you asked this loop. Then you ask, this guy, what is your potential here? So he says, because this guy has key characteristics like this, and that guy have committed that, I would be almost at the same potential as here. Because why? The difference is infinitely amplified. That amplification is being fed back. So the only way this can stabilize is if this point becomes equal to this point with the derivation factor of difference being by infinity. But infinity is never the case. Second order system says that there is a limit on open loop bandwidth, no open loop gain. So this are at virtual ground. You would have seen this virtual ground concept in your classes, right? So when they are at virtual ground, what is the potential here? 0, because this is 0. Once this is 0, you also know that no current can enter here, which explains one thing. Whatever current is supposed to come from here to here, the same amount of current is supposed to come from here to here, right? Then only this point is 0, na? Agree? Correct? That is how the question you may get in interviews is, how do you explain the virtual ground concept? Very, very solid fundamentals. If you get this right, you can analyze anything. You can analyze control systems, you can analyze your integrators, differentiators, anything. This is a very solid concept. So get it clear. So for all this guy's commitment and this guy saying I'll be virtual short, it says that the current flowing in this path is equal to the current flowing in this path, because nothing enters here and this is 0 potential. Now, as somebody said, V out by V in is the gain. V out is current multiplied by the resistance, because this point is at ground, correct? This point is at ground, right? So your output voltage is here. If you put a resistor to ground, what you would say is this voltage is equal to the current flowing through the resistor multiplied by the resistance, right? And we also said that that current will be equal to this current, correct? So that current is nothing but V in by R. Now if you take the ratio of V out by V in, the V ins get cancelled off and you get to minus R2 by R1. That is what is the gain of an inverting amplifier. Now an exercise to you going back with this concept, try attempting the non-inverting amplifier. What is the gain there? 1 plus RF by RN. You will get to it. Go the same process. There it is not virtual ground. There the concept will be virtual short, because no more the inverting terminal is at non-inverting terminal is at ground. So you go by virtual short concept. Cool. So this is nothing related to what we are. I'm just brought in here for a fresher. Time. 1 o'clock another program, and what's the time now?
12:40.
Okay. So I'm going to slightly write faster. And we can even cut out in between if needed. 5 minutes we will wind up. Okay, so we are talking about the GPS receiving stuff. There is some aspect called ephemeris. Ephemeris is a precise orbital position of individual satellites. This is that message we talked about. We are correlating with the PRN and then making it out. Then we have an almanac. Almanac data is a collation of 24 satellites sent by every satellite. So each satellite sends almanac, ephemeris, and ephemeris is all about myself. Almanac is about my group. Okay? And then you have the pseudo-random number code, which we did discuss how you lift from a noise floor my signal, and the atomic clock data. I have to say at 11:28 I said hi. So that data. This would be too much, I think. I'm skipping this. Oof. No, 5 minutes we will not be able to. Okay, so I'm skipping two of the important stuffs in constraint of time. We are going to look at another one aspect called dilution of precision. Now, as engineers, we had a problem statement. We all together decided all the stuffs. Now we are going to look at a problem with our initial way of implementing. Now you assume that there are 4 points required to triangulate. Think of a situation if all those points are one above the other. Okay, if all the points are one above the other, what would happen? The distance would be same, right? And you cannot triangulate because your entropy in your measurement is low. You are not far. Every satellite is one above the other, right? So that aspect is called dilution of precision. The dilution of precision is you thought everything will work great, but because of a scenario, if this was the case, I have good entropy. I'm reading it from different Cartesian coordinate system. But as soon as you start getting valid satellites, you said that we only need to have 4 satellites, but that satellites are being very cluttered or clubbed. Then what happens? You don't get a good trilateration. So that gives you an aspect called dilution of precision. And dilution of precision comes in different ways. One, what all we measure? We measure the XY coordinates, we measure the altitude, we measure the time. So we have a GDOP, which is geometric dilution of precision. This is a collation of how bad your time is interpreted and how bad your XY coordinates are interpreted. So that is called GDOP. The PDOP is positional DOP, which means it is only dependent on the XY coordinate, how diluted we are. Okay? So that is called PDOP. The HDOP is the horizontal one, which describes the influence of satellite geometry on the position along the plane. Then we have the VDOP, which is talking about the dilution in altitude, and the last one is TDOP, where your time gets diluted. Okay? So these are the aspects, and pictorially how we represent this. If the satellites are very far, your triangulation area is small, so you are better in dilution of precision. So lower the dilution of precision, it is always better. And that comes from the entropy of your measurement. And higher, you get into more of a trouble. Quickly looking at what are the issues of good side of GPS, which is being wrongly used by other engineers, is you are an RF signal. If I generate a stronger RF signal, my capability of the receiver to receive goes down, and that is what is jamming. So it is very easy to jam a GPS thing. What do you need to do? Whatever is the carrier wave, put simply a continuous wave at highest power. None of the receivers can do anything because the noise floor is much higher, because the noise is very high. You cannot do that 80 dB lift up or 50 dB lift up. I wanted to spend some more time here, but with time, I'm cutting off. We have one aspect called spoofing. Spoofing is, you are driving and all of a sudden you see 4 satellites. One bad guy is able to replicate that satellite for some time in a higher power. So your tracking algorithms try to fix to the highest power satellites. All of a sudden he starts drifting the position. So Instead of actually GPS locking into your tracking and correlators, you start locking into the pseudo signal what is being generated. So that is what is spoofing. You guys are really Gen Z, I know you are really into AI. This is an awesome part to write papers with AI. How do you deal with this kind of a situation? Spoofing. Because spoofing by implementation, as engineers we first discussed the problem we made as solution space, by implementation cannot be addressed there. You have to add a wrapper on top of it for the correlators, and that should be AI, and it can be a very, very good stuff for taking for your papers.